The reverse transmission is S12, which is B1 over A2. Now, in general, the device under test can change both the magnitude and the phase of a signal. And so as a result, the scattering parameters, this S11, S21, and so forth, are complex numbers, since a complex number can change both the magnitude and the phase of a mathematical expression. So mathematically, this implies that we're going to have vectors in a complex plane. Remember, we had phasors, and we'll have that here as well. In 3300, we had phasors that we discussed. So in the complex plane. And this is actually exactly where the word vector comes from in VNA, is that we have vectors in a complex plane. So in contrast, a scalar network analyzer would only provide information about the magnitude of a signal and not the phase. The University of Utah Electromagnetics Lab is equipped right now with 6 Keysight PN371A VNAs. And these are from Keysight. And a couple of images of this VNA are shown here. So we have 6 of them in the lab, and this device has a frequency range of 300 kilohertz to 6.5 gigahertz. And it's capable of taking several measurements every second. As you work with the device and manipulate its various connectors, please be mindful that this is very expensive equipment. And to help protect the VNA, there is actually no need for you to touch the VNA, except to maybe push the power button on the front of the panel. All the interaction you're going to be doing with the VNA will be through the computer that will also be on the lab bench. An electrostatic discharge can damage the VNA, so it'll be important for you to wear a grounding strap when you are working with the VNA. And this is going to be discussed more in the lab write-up. When you arrive in the lab, there should be 2 purple cables connected to the 2 ports of the VNA. So here is port 1, here is port 2. So you will see 2 purple cables connected to both of those. And these are relatively high quality cables. They're designed for very low loss over a large bandwidth. And so these are much more expensive than the device under test, like the general use cables that we're going to be connecting to these purple cables. So be especially careful when handling these purple cables and don't forcibly bend or twist them. The minimum bend diameter is 8 to 10 inches. So you don't want to bend them any more than that, and try not to get anywhere close to that. Also, avoid simultaneously touching the inner and the outer conductors of the coaxial cables or any parts that are connected to the VNA. At the ends of the purple cable are extra adapters, and that's where you're going to be actually making your connections to the VNA. So you're never actually going to be removing or changing the purple cables. Those are going to stay connected to the VNA, and it's the adapters at the end of the purple connectors. These are going to serve as connector savers, and these are intended to serve as cheap replaceable parts. I'll put here replaceable, cheap, because simple mechanical operations like screwing and unscrewing the connectors can eventually wear them down, and it'll degrade the performance and wear down the connectors. So that's why we have those at the end of the purple cable, so we can replace them as needed. Now, in this course, we're going to be measuring up to 1 to 2 gigahertz. And so we're going to be hand tightening. Put exclamation marks there. Don't use a general purpose wrench to tighten any connectors that can easily damage the threads. A calibrated torque wrench is often, it's used at higher frequencies than what we're going to be operating at. So we're going to be hand tightening any connections in this class. There are many different varieties of mechanical connectors. In this course, we're only going to be using the ones that are shown here. And on the left here, these are called sub-miniature version A. And for short, you'll see that called SMA. And on the right, we have 3.5 millimeter connectors, which is basically an advanced version, an advanced variation on the SMA. And the SMA can be identified by the thin white layer. It's a dielectric insulation layer around the core. And the 3.5 is filled with air. So generally speaking, the SMA connection tends to be rated for frequencies below 18 gigahertz. And the 3.5 millimeter connectors tend to be able to operate up to as high as 34 gigahertz. The 3.5 millimeter connector also tends to be better machined, and it's more expensive as a result. Otherwise, the two connectors, SMA and 3.5 millimeter, are perfectly compatible with each other, and they can be used interchangeably. But bear in mind that the 3.5 millimeter is relatively fragile, and a damaged SMA component can mechanically destroy the 3.5 millimeter if you force them to connect. So be careful about the connections and the quality of the connectors before you start to connect things, and be especially mindful of the fact that they could damage each other whenever you connect the 3.5 to an SMA. And don't hesitate to ask your TA if you have any issues or suspect a connector that might be damaged. The gender of the connector is defined by the inner conductor as being male or female. And it can also be helpful to visually check each of the male connectors. It's not uncommon for the inner conductor on the male conductor to be pushed back into the connector shell, and this causes the inner conductor to not make good contact. So, and that's probably the most common problem with the connectors and cables that you'll get that will lead to confusing results, especially if this is just a little bit pushed back into the connector, or it looks okay, but it isn't actually making a connection. So that's the main thing to watch out for as you're using these pieces of equipment. A couple of other important notes about the lab equipment. This was mentioned once before, but don't touch across the two conductors. I'll write that here. Don't touch. We don't want an electrical connection between the two conductors. Also, periodically, the connectors need to be cleaned. And that's done with alcohol and a cotton swab, and directions for cleaning the connectors are included on the help and resources page for this class. All right, so we're thinking about using a VNA to build our proof of concept demonstration of the SSTDR system. Maybe we work for a company or at a university that already has a VNA, so we can go and learn how to use it and tinker around with it. In our case, we'll have access to one in, of course, the labs of this class. But otherwise, if we didn't have access to a VNA, maybe we could, to help prepare us write a proposal, we could have a friend or a colleague who would let us try one out. But either way, it would be good to gain experience with a VNA so we could write a stronger proposal and knowing what we're doing. If, however, we did not yet have access to a VNA, we could propose that we could purchase or rent a VNA. Sometimes you just can't get access to the equipment that you need that you're going to propose using. So in that case, you would just include the cost of the VNA in the budget, and you'd have to wait until your grant is awarded to tinker around with it and use it. Okay, well, we've covered some introductory material here for the next lab, and in very shortly, you'll be getting some experience using the VNA.